Our planet has been nurturing us for millennia. It can keep sustaining us, but its resources aren't limitless. We need to act now to protect the planet for future generations and make our societies climate resilient. The European Green Deal is the EU's commitment to be the first climate-neutral continent by 2050. It means radically transforming how we do things, reimagining urban landscapes by restoring ecosystems and giving space to nature. Finding greener ways to move around. Eating healthily while giving back to the planet. We have an opportunity and a responsibility to set Europe and the world on a more sustainable path. Research and innovation hold the solutions. Together, let's bring them to life.
Well, good afternoon to everyone who's joining us here in Southeast Asia, and a late good morning to everyone joining us from Europe. You are joining us for this session of the European Research and Innovation Days ASEAN 2021. My name is Susanne Ransovasu, and I'm here with my colleague, Dr. Jenny L. Mako. We are both the regional coordinators for the EURAXES project. Now, EURAXES is your gateway to research collaboration with partners in Europe. And we are also the ones that are running this event series at the moment, the European Research and Innovation Days ASEAN. And I know a lot of you have already been joining us for the past few days for these sessions, which are this year focused on the very important issue of climate change, innovation, and global health. We had a lot of dialogues already, and we have an exciting session ahead for you because we're looking to hear from a project that is really turning lab ideas, research ideas into real world applications. This is a great example of a very successful collaboration between the European Union and ASEAN, who, as we know, have a long record of working together in science, in research and innovation, and are, of course, working together ever so closely now that it comes to those joint objectives of carbon neutrality, finding solutions to combat climate change. So the project that we are very happy to introduce you to today is called GreenTech. And GreenTech is really dedicated to the transfer of green technologies. So in this session today, we'll hear about some of the very real solutions that this project has produced. It is my pleasure to introduce you to the moderator who will lead you through the session today. Is Dr. Michael Brown, and he will then in turn also introduce you to these exceptional panelists today. And so again, we have a very exciting session ahead of us. If you have any questions, please do make use of the Q&A box at the bottom, and we will make sure that we will address your questions. Now, enough from me. Michael, the floor is yours.
Thank you so much, Susanne, and also from my side, welcome to all of you. Good afternoon to our friends in Asia, and late good morning to our friends in Europe. And I will be your guide through this session now. We will touch briefly, first of all, on the GreenTech project, which Susanne just mentioned, to give you a brief introduction of how this project works. And then we would like to show you two examples of EU-ASEAN collaborations, which we have instigated and where we have great scientists and great companies also working together to bring green technology to life. So if I may, please allow me to start with a very brief introduction to our project. Can you see my screen?
Yes, we can. Perfect.
Thank you, Susanne. Okay, then let's move on. So, what are we after? We are after sustainability. But what we do is we need new solutions. You see, we want less waste, we want less pollution, we want to recycle or to reuse in any way all the waste which we are producing. In fact, we want a better life for everybody. But the question is, how can we achieve this? And so there's a lot of talk about that we have to move from a linear economy where you have cradle to grave approaches, where you produce plastic, to stay with the example of plastic, you use the plastic and then you throw it away and something happens with it. And we want to move from this to a circular economy where either we don't produce any waste or we can use all the products at the end of their lifetime. We can bring them back into the beginning of the cycle. But what we know is that this requires new technology. This is not something which you can do easily. So you see, there's many possible technologies we can speak about and think about. To stay with the plastic example, we can replace conventional plastic by biodegradable plastics. This is something we're working on. Then we can think about waste to value, where we are working. You have seen an example in the film before already, where, for example, we're thinking about how can you use the residue from the processing of fruit and vegetables, where you have the peels, where you have the seeds. How can, instead of throwing these away, because today a lot of these end on the garbage dump, how can you reuse them? But then there's also the high technology in manufacturing. For example, we can use robots for better work conditions. You can use artificial intelligence to help us manage manufacturing in a way that we get zero waste. And the last important thing is, in our days, we need to think about new medical solutions for the pandemic in which we are all at, and which is also the reason why we're meeting online here instead of meeting in Hanoi, instead of meeting in Kuala Lumpur or wherever else we could meet here. So we are online here, and this is something also we need to think about. And the objective of our project is to bring together the actors who can bring these solutions to life. So what we need to bring together is the researchers. Research is producing these solutions. Then the private sector, the enterprises, they can take the new technologies, but only they are able to implement them on a big scale so that really we get tangible benefits from it. We need to work with the communities, because waste, to stay with the plastic again, is something which affects all communities, and where we need the communities' collaboration also to cope with this waste. And finally, we need the policymakers who must create the right conditions for doing this. And the reason why I'm speaking here is that we take a new, fresh approach to this by trying to instigate and to support scientific cooperation and technology transfer between Europe and ASEAN. Why do we do this? Because on one hand, many ASEAN states are in a transition from a resource-driven economy, which is built on cheap labor and natural resources, to an industrial economy, to an innovation-driven economy, where they need innovations, where you need technologies for sustainable growth. Because they also need to move from a past model to a sustainable growth, to green growth, which makes the best use of resources, which keeps care of our environment, which protects workers and all our lives and improves our life quality. And for this, there's a need to upgrade technologies and innovation capacities. And the natural partner to do this is Europe, because in Europe, we have, and I say we because I am European, even if I've lived in Vietnam for the last 10 years, we have a lot of technologies available, And we have big programs like Horizon Europe, an 80 billion framework program to support research and development. And this yields a lot of new technologies and new opportunities. So you see, Europe and Asia are natural partners. And this is why we have started the GreenTech project. And the GreenTech project tries to do two things. The first is we try to build communities. We try to bring together the researchers, the innovators from Europe, from Asia, from Southeast Asia, on joint platforms to speak about the problem. So we had 6 webinars, for example, on plastic waste. You can see these webinars on our website. And this is one thing. We try to build such communities so that we speak together, that we work together. But then we also want to make collaboration really work by pursuing 3 pilot projects. We try to demonstrate in 3 pilot areas that Europe and ASEAN can work together for mutual benefit. The first pilot, which we're working on, is plastic waste, where we transfer technologies, where we stimulate research cooperation in order to mitigate the plastic tsunami which we are dealing with, or to avoid it in the future. Our second pilot project is sustainable manufacturing, where we try to find new ways how to move towards a resource efficient and environmentally friendly manufacturing environment, which does not pollute the environment, which makes the best use of resources, which produces 0 waste. And the third one is to deal with our actual situation, to deal with COVID-19 pandemic, where also we all need new technologies. We need the vaccines. We have seen vaccines are a big success story now, but we still have a long way to go because Southeast Asia is still short of vaccines, and Southeast Asia must improve its capability to react to future new pandemics which may happen. And so we from the European side, we need to help Southeast Asia to work with this, but also we can benefit from the research and from the initiatives which are going on there. And we are doing this in our pilot phase, where we are at in these 3 pilot projects, which are, and where we're collaborating especially with the Philippines on plastic waste and with Vietnam on sustainable manufacturing. But in the next phase, from next year on, we will roll this out to all ASEAN member states. And I would here already like to invite all of you to come to us if you have an idea for projects which fit into this theme. If you are looking for a European collaboration partner, if you're European, you're looking for an ASEAN collaboration partner, drop us a message and I promise we will care for you. And what I would like to do now is to hand over to my colleagues who will show you 2 practical examples of the type of projects we are instigating and supporting. The first one is a collaboration between the Max Planck Institute for Chemistry and the University of San Carlos on the Philippines, which are developing a low-cost ventilation technology for COVID-19 protection. Max Planck has laid the scientific foundation and proven this, and now we're trying to transfer this technology to the Philippines to adapt it to a tropical environment, to the different conditions, because this has a lot of benefits, as my colleagues will explain to you. The second one is high technology, where we would like to show you additive manufacturing at work. So we will introduce you to new materials Bayreuth Technology Center, which is specializing in additive manufacturing, which is doing state-of-the-art research and also technology transfer. So New Materials Bayreuth will introduce you to additive manufacturing, state-of-the-art, as well as to their model of how to cooperate between science and technology. And then finally, the ASEAN partner with whom New Materials Bayreuth is working at this moment, the APEC group, Mr. Henry Wu will then show you from the industrial viewpoint, what is the benefit for industry? How does industry benefit and work in collaboration with research? And how does industry make these new technologies work? I'll stop here for the moment. I will hand over now. The last thing, one word, as I said before, you are all cordially invited to drop us messages here in the chat or to send me an email. You see my email on the lower right side here. If you have inquiries, if you have a project to forward. Thank you very much. I will stop here now and hand over immediately to Evelyn and Frank to present the first example, the University of San Carlos Max Planck Corporation. Thank you for your attention.
Hi, Evelyn. Will you take over for the first slide, please?
Yes, thank you so much, Michael, and thank you, Frank, for joining me in this session. Maybe, Frank, you can press the slideshow, please?
Here we go.
Yeah. So today we are going to present to you a very nice, exciting collaboration between Max Planck Institute and in Germany and University of San Carlos in the Philippines. We are going to adapt and develop and implement test beds here in the Philippines for low-cost ventilation systems which are applicable in the tropical regions. No, basically here in the Philippines, and we expect to roll this over to all other interested and willing ASEAN member states. And for now, we're test bedding this to come up with low-cost ventilation systems which can address and the risk of infectious aerosol-based virus transmission. So I'm Evelyn Tabuada, and I come from the Philippines, and I give you now the floor to Dr. Frank Helis of Max Planck Institute for Chemistry to lay down and show to you the foundations of this ventilation system, and I will take over before closing to show you some examples that we are going to work on. So back to you, Frank. The floor is yours.
Okay, good morning, everybody. On the MPI side in Germany, we're doing basic research on aerosol, air quality, climate, etc. On COVID-19, up to now, we had lots of studies of scientists on related issues like infection risk, face masks, respiratory aerosols, and of course, venting methods. I'm personally involved in this venting business. Venting of classrooms was one of the first large problems we had in Germany, which we have worked on. And here we did comprehensive mechanistic experimental and modeling studies regarding free window and mechanical ventilation. We are in cooperation and exchange with schools, administrations, physicians, building and venting experts, national and international. This is about our institute, where we're doing basically the integral understanding of the planet. We have 4 departments, about 300 staff, and atmospheric, climate, particle, and multiphase chemistry. So it's really about the whole picture of the planet. This is typically what we're doing if there's no COVID-19. So this is from all our studies all over the world we did with ships, aircraft, on large towers in the Amazon or in Siberia, for example, in the years 2014 to 2017. So now coming back to COVID-19, the first thing you have to understand is how the virus works. This is a very nice, the top graph is a very nice graphic from Christian Drosten in the German Time, Zeit magazine. And basically what you see here is, here you have the time, so to say, 0 when you start having the first symptoms, when you realize maybe you're sick 5 days before you get infected, 4 days afterwards you get your diagnosis, and about 7 days later the authorities send you to quarantine. So this plot is something like the virologist's view with log RNA axis. So if you put the ln axis here, which is the view of an aerosol scientists, because you're interested in the dose, which actually the person to be infected will receive, then the result is the lower right plot. What you see here is again the 0 line, that about the infected person distributes about more than 80% of her viral load before actually having symptoms. And this is the great success story of this virus. The spread is completely independent of lethality. Becoming more deadly is no disadvantage for the virus. So we really have to keep that in mind to think about what we can do about it. Now, before you can start doing any calculations, you have to have an idea of what the viral load in typical people is. For example, of course, we are interested in small children and school children. Here you got a very nice study of Jones, which is also in Drosten group, kindergarten, elementary school, high school, and university. And basically what you see is that there's no significant difference in viral load. And sometimes they test it early enough to actually see these 10 log 10 even in small children. 10 log 10 per cc in your respiratory airways fluid. Now, let's look at how this infection pathways actually, how this infection actually works. Here's a very nice graphics from Pölker et al., also Max Planck Institute for Chemistry. On the left side, you have the emitters. On the right side, you have the recipients. And basically, you can specify 3 different routes where it works, how you can infect people. The one is the near field droplet route. That's by directly spraying droplets at the recipient. Then there's a near field aerosol route that can happen if you, for example, walk after somebody in close, not no big distance. And then there's a far field aerosol route, which is basically what you only have in indoor environments, where actually the virus spreads over the whole room, and it basically doesn't matter too much where you're sitting in the room. And you can be infected even without direct contact or outside these 1.5 or 2 meters safety distance. Now, since we know all this, we can put real numbers there and really distinguish how these pathways work. The first interesting is just more or less the red numbers you can be interested in. And the size volume of a respiratory aerosol is between 5 micrometers wet and 1 micrometer dry. The average inhaled variance, this is typically for a classroom calculated. If you have only aerosol, no vending, so this is only about indirect infection, then it's about less than 10 per hour if you breathe or speak. If you start singing, it's much more than 10 per hour. So it's 10 per hour, 10 variants per hour, 10 infectious particles you actually inhale. The average minimum droplet containing 1 virion is 30 micrometers. That you directly see that the 1 virion, which is 0.01 PFU, this kind of droplet would already settle so fast that it would not lead to indirect infection. The minimum droplet diameter containing the infectious dose is about 0.15 millimeter. And the infectious content of a 0.7 millimeter saliva droplet is about 10,000 virions. So, and now it's easily to distinguish things. The indirect infection in the far field is aerosol, which is smaller than 10 micrometer. It can stay 1.7 hours infectious in the air, and the risk can be mitigated by venting. In case of the direct infection on the near field, it's droplets which are larger than 30 microns. Most of them contain already a virion. The sedimentation is so fast that they stay max 1 minute in the air, and this risk cannot be mitigated by venting. So for this, you can actually use to actually calculate under what conditions your infection risk is what. You can use, for example, our aerosol transmission risk calculator of Lelyfeld et al. 2020 on iChirf. It's also online. It's given here. It's an example result. So now to access actually what happens in classrooms, we need models. And the first thing we did 2 models for different timescales. One is our day model, the second resolution, which we determine infection prevention, air quality, and comfort with. The second model is a year model with our resolution. And this is basically only for sustainability issues and also so energy and energy efficiency and something like that. And also we need these data as input for the day model, for example, for the daily average cycles. The data we typically take from DVD, from Deutsche Wetterdienst. So this is real world data, which is typically modeled with. So now if you put all the mitigation strategies which are followed in Germany into one simple plot. This is simply all the basically winning methods you could think of which could mitigate infection risk. Then on the lower axis, you have your mean CO2 concentration. So that is something indicative of your room air quality. And on the left axis, on the vertical, you have the dose reduction compared to the work safety rules we have in Germany. Now this this yellow point here in the middle of the plot, basically in this cross here, this is the work safety rules. And you can see that for example, the mechanical ventilation heat recovery units, which is about these red points here, they are in this range, and the weaker ones are down here. And then the air filter technologies are here, so they have not a good air quality, but they have some dose reduction. So basically what you see is that all the mitigation strategies we have concerning venting we have in Germany is more or less like plus minus 25% of what was necessary already before the pandemic. Yeah. So basically, it's not that there happened very much. It's just that now we follow the rules we had all the time. Of course, you can do cost comparisons of different measures, and then you see, of course, that the full-blown mechanical ventilation heat recovery units is like a factor of 10 more than a simple device, and then you can give economical and ecological figures of this, and then you see what your footprints are in terms of CO2 and in terms of money. So our work was basically to follow what was going into our public as information from the Federal Agency of Environment. And since we didn't understand everything which was distributed there, we started to actually measure things, you know, in the classroom. And the interesting things for us to measure was really compare air exchange rates of shock, continuous, and mechanical ventilation procedures, and then really measure shock venting efficiencies in practice versus the recommendations. And as you might know, in Germany, we have a big discussion about air cleaning technologies. And here's a plot where we actually modeled that for different types of rooms. The one on top is one which is not ventilated at all. You see already there, you have it's limited basically by the lifetime of the virus and by the sedimentation and infiltration of the building. The blue curve you see here is a typical room which is called like not that well ventable. This is where you have too few windows to actually open, and the red curve is something like what you end up with in a well ventable room. And what you can see here, if you compare simply the RNA concentrations in the room in more or less steady state, then the typical dose reduction factor on these technologies is if you compare it to the not ventable room, it's maximum 4, and on the not very well ventable room is at max 2. So the 90% dose reduction, which is always said in the public, is not possible in real life. It's more like smaller than 50% realistic number. So our classroom looks like this. This is where we actually do real experiments. Most of it is mechanistic because we were interested in really in where the air goes, where it flows, how it's distributed in the classroom, and looking for venting efficiency really rather than actually a real field survey. So this is basically not well ventable room. That's why we did it. And what turned out is that this category 2, the not very well ventable room, works smaller than 10 degrees C. And the Cat 2 room works with window ventilation, with continuous ventilation, at temperatures smaller than 15 degrees C. So at these temperatures, below these temperatures, it's easy without ventilators even to reach the to achieve the infection risk mitigation, which is required by our federal agency. So now the interesting thing here is, I wrote the citation here. It has to be noted that good ventilation alone cannot prevent the transmission of SARS-CoV-2 from one person to another in general. This would require very high air exchange rates, which cannot be realized in practice. That's what they say even. Therefore, in rooms occupied by several people, additional measures like face masks, distancing, and appropriate scheduling are especially important. And now the idea for us was really to look at, is it possible to find ways to reduce pollutant concentration without raising nominal air exchange rates? Because there is a physical and, of course, also an economical limit on this. Especially in Germany, where we put lots of heat out of the window if we start venting like crazy. And actually, this is really known for 30 years, and it's sitting in the textbooks. You just have to look at it. This is on the right side. On the left side, it's a small sketch. You put in the cold air at the bottom, and you take the warm air out of the top, and this gives you this stratification in the room. And on the right side, you have a plot from this textbook where you can see that mixing ventilation typically has a venting efficiency on the order of, let's say, 1. And this specific displacement ventilation can have a venting efficiency on the order of 5. And this directly translates in an infection risk reduction of a factor of 5. And then we thought, okay, why should we leave this factor out of the calculation? So what we did was really simple. We took a sheet of plastic sheet cover onto our lower windows and had the air coming in below into the room. You see it on this picture here, below the heaters, right? And this is the cover you can move, so they can easily access the windows for opening and closing. And it's really, we were really amazed about this measurement. What you see here is measurement on top of the room and measurement in seating height, where the person actually gets its air, its breathing air, and you see that can be up to a factor of 5. And the nominal air exchange rates here is about only 4 per hour. And what you actually, the infection risk actually you reach is something like 12 to 20 per hour equivalent air exchange rate. So these are real factors. So then they did some modeling on how, so to say, if you say what happens, you have one infected person in the classroom, of course, you don't know where it's sitting. And how does actually the plume of this person actually move through the classroom, and how is it diluted? And what you can see is it stays pretty much concentrated with this system we had in our classroom. It stayed pretty much concentrated. So most of the people, most of the time, actually don't see this plume. So also from simulation, this seems to work. So the simple ventilation system we proposed then in Germany was, it's decentralized. It has lowest requirements. What you need is a wall socket for the ventilator, and you need 2 tilt windows. It's lowest cost. It's possible refit in existing buildings. You don't change any facade. You don't have any trouble with authorities. You have the lowest operating costs, no or only cheap filters preferably. Simple, individual, and intuitive operations. Switch on the fan, open the windows. Then you simply take advantage of the physics. You align the physical, the buoyancy-driven, and technical flow direction. You reduce the convective mixing of intake and exhaust air. So what normal mechanical ventilation does, they force it. They want this. We don't want this. We try to reduce it. So we go very much the other way. And we reduce the pollutant concentration by increasing the venting efficiency, which is well known, actually. I mean, it's done in big, large rooms like concert halls, and so they use, also professionals use this technique. And of course, we distribute the intake air and targeted exhaust air. So the highest possible venting efficiency with least possible air exchange rates, save energy, low noise, minimal sensible winds. The reason why ASEAN is so interesting for us is actually the combination with air conditioning. So this is actually why we're really interested in this project. Yeah, the collaboration. I guess I can already switch back to Evelyn to take over the talk here. Evelyn, talk. Okay. Or now, are you presenting yourself, or shall I switch the slides?
You can keep the slides, Frank, and if you don't mind, you can switch it.
Oh, no problem. Yeah.
Yes, thank you. So thank you so much, Frank, and I hope all of you has been able to grasp what Frank has been presenting. No, since it's a little bit complicated at the beginning, but later it's all just very practical and pragmatic. Also because Frank and his team has showed the economics and ecological advantages of such a design. So the Philippines, on behalf of the Philippine government, we presented this project, and they are willing and they are now funding the project for its deployment to the Philippines. So this collaboration with Max Planck and USD has now put into the wheels of motion. So the general objective is really just to further demonstrate the viability and effectiveness of the design of this low-cost ventilator. As Frank has mentioned, it is very interesting in the ASEAN region because of its tropical conditions and the fact that the tropics is also paired with air conditioning, and it's almost opposite with what happened in Europe, particularly in Germany. And also because in the pandemic, it is very important to really to take care and address the health issues and the needs of people, no? Especially in classrooms with the children. So the specific objectives is just a simple adaptation, technology transfer, and also we anticipate some modifications of the design for classrooms, especially in the public classrooms where there are a lot of children at risk. And we extend the project to essential business offices such as government agencies where personal transactions are really required. And then we also extend it to public transport vehicles as buses and jeepneys in the tropical areas like the Philippines, and more so in order to fast track economic recovery. We also want to extend this adaptation to small manufacturing facilities like the small medium enterprises in the food industry, electronic industry, garment industry. What have we here in the Philippines? So we assess and evaluate the performance, viability, sustainability, and then have it ready for massive deployment here in the Philippines. And then we go back to the platform for dialogue in the ASEAN, and we will in that instance then we will disseminate this technology, what we have found, and then ASEAN member states can also adopt and learn from this if they want to and if they are interested. Next slide, Frank. This is just very quick. So this is a typical public classroom. So as you can see, it's very small, and then windows are just the way to ventilate the classrooms. Next slide, Frank, please. And then this is the inside of the classroom. As you can see, we take a picture of a kindergarten classroom. There is not actually electric fans here, so just normal ventilation. And we see that after 5 minutes or so, then you will be sweating here. And then when electric fans are installed, then it will be on the sides like the stand fans and so on. So we are very keen on really investigating how the simulation of this kind of spaces, enclosed spaces, would affect the flow of aerosols or droplets. Next slide, please. So here is another classroom. As you can see, we emphasize the ceiling because there is also another way to ventilate, but that is coming from the ceiling with these fans here. And then from the design, it is really not a very good way to do it because then it would promote air circulation, and with aerosols or virus droplets, it could probably also increase virus infection. So we have to study that. Next slide, Frank. And then here is also a typical classroom with a desk of students. So how we are going to space out students and then design and install the low-cost ventilator system. So very interesting spaces indeed in terms of classrooms. Next slide, Frank. So here is another typical classroom using chairs and desks where students or people can rearrange the chairs and desks so they can talk to each other. They have groupings, peer learning. So we also wanted to see how the dynamics of people going around inside the classroom would affect ventilation with a fan here, there, upstairs at the roofing, at the ceiling, and then whether or not that is indeed very nice or very good or will promote proper ventilation with reduction of virus infection. Next slide, Frank. So this is another picture of an air-conditioned classroom and then computer. This is a computer room in a university setting, and we see here that with air conditioning, there is just an exhaust which is not found seen here, but with this, it could actually also affect the proper ventilation and could also recirculate aerosols and then increase virus infection. So we'll see how the ventilator would really perform before and during this kind of simulations and demonstrations, and share to you the results. Next slide, Frank. So here we acknowledge, of course, the people who helped in this process. And I also would like to acknowledge the Philippine government, the Department of Science and Technology, and specifically the Council for Health Research and Development, because they really want and they are very keen of doing this project as soon as possible. So we already started this project. All the memorandum of agreements, the contracts are already signed. The money is already along the way downloaded or transferred. And then it's a matter of really doing this properly and closely. So therefore, it would be very interesting to come back to this kind of platform and report to you what are the results and the findings we have when this low-cost ventilator system is applied in ASEAN or tropical regions. It would be very interesting really also from our end, because these are low cost and also easy to do, easy to install kind of ventilator systems. So therefore, it can be deployed easily in all parts of the country. With that, thank you so much. And I now open the floor for questions. I think we have a few minutes to entertain a few questions. Thank you so much on behalf of Frank and myself, Max Planck, and the University of San Carlos and GreenTech. So,
Evelyn,
yeah. Yes.
If I may, I just see one question. There's a question about these IC systems. Do you need to install filters to minimize the percentage of infection here, or is it really just the airflow?
Actually, yeah, Frank, maybe.
Yeah. No, it's simply we just exchange the air, and since there is no penalty on it, we don't need to filter it.
Thank you. That's clear. Mm-hmm. Then may I ask maybe one question by curiosity to both of you? So far, in trying to collaborate in the days of COVID-19, which make it very difficult to travel, how easy or how difficult do you find it to collaborate over 10,000 kilometers without ever having met physically?
Yeah, I could answer that question probably first, Frank. So actually, this is very interesting because it's also cost effective on one hand, as we discovered it, because we could always meet with Frank on Zoom and we could have hours and hours and hours of discussion about all the scientific foundations that he has laid out for the ventilator system. So that's one. Second one is, the second part is that, as you have seen in Frank's presentation, he and his team has already come up with a simulation calculator, so we could actually play with it. The team here at the University of San Carlos has played with it already and has made already some inputs on the different types of conditions that are possible in the Philippines and in ASEAN for that matter. And they are really working, and it's really very exciting. What is the most important challenge is when we see Frank, for example, in Max Planck, the team really wanted to see him and learn from him as much as possible, because the idea is to get as much information, knowledge, and so on from Frank, learn from it, and be able to transfer it directly to the Philippines and so on. So that is the main thing that happens. But so far, so good. And the team in the Philippines here plan to visit Max Planck next year. Hopefully, the COVID will ease out, and the travel restrictions would also ease out. And then the funding is also good already. Frank, if you can add more.
No, I think this is comprehensive. No, I really like it. Actually, the pandemic makes me much more efficient than I was before. So it's really much easier. No. So if all these projects, I couldn't do it if I were physically in the institute, actually. So I work from home, basically. Yeah.
Thank you.
And I appreciate it.
Mm-hmm. One last question to both of you. I would like to know about what happens after the project will be completed. Evelyn, could you maybe say a word about how other ASEAN member states and how as many schools and pupils as possible can benefit from this? And Frank, maybe you could say a word about what is the benefit for Max Planck to cooperate with a partner in Asia like this? You mentioned it briefly, but maybe you can say a word more about it.
Okay, so me first. So to answer your question quickly, Michael, actually the Philippine government is very interested in it. That's why they say immediately yes when we offered this, when we submitted the concept note and asked for funding. That's one. Second, they want it yesterday, meaning we want to implement the project as soon as possible and implement it as soon as possible so that children can go to school immediately without this anxiety of them being exposed to COVID. So that's another thing. And when we talk to our other ASEAN counterparts, they are also very interested in it with the same reasons, no? And then also that we want, especially also with the classrooms and the government offices, the public transport, and also the small manufacturing facilities, because these are key enclosed spaces which would actually, when open up, would fast track the economic recovery. And this is very important for ASEAN, especially for the Philippines, for example, in order to really address this pandemic issue.
Thank you. Thank you.
Frank?
Yeah. For me, as we said, our institute is very much interested really in climate change and in mitigate the problems we have here. And one of the reasons for this project is also to explore, and this is what we are now doing. We are going more into the direction energy. You know, and really find out, and this is also for us very interesting, having data from tropical sites or subtropical sites to really find out what the footprint would be if you combine this air conditioning stuff, or if you roll this out more than you have maybe now, what would be the actual CO2 footprint on the planet. So we are really interested also in future on this, and we hope that a couple of these rooms or representative rooms will be equipped with measurements for the next, say, 10 years or so. Yeah. So we are really interested in collaboration there.
So thank you very much to both of you. And I can assure you, when I look at the chat, you will not be short on further cooperation partners in the ASEAN region when I look at the chat. Thank you very much. For time reason, I suggest we just move on now to our second topic. And we have deliberately chosen these two examples to show you, on one hand, as Evelyn and Frank have shown you, that innovation must not always be the latest high technology, that sometimes a sound scientific base combined with very simple cheap means can achieve remarkable things. But now we're moving to a high technology era, which is additive manufacturing. I would like to introduce you to Professor Volker Altstedt of New Materials Bayreuth, our first speaker on this subject, who will then pass on to the others. Volker, please, your turn. Thank you.
So I hope you can hear me, and I also hope that you can see my presentation. Well, my name is Volker Altstedt, and I'm a professor at the University of Bayreuth and the CEO of a state institution with research mission, which is called Neue Materialien Bayreuth GmbH. This means translated New Materials Bayreuth Ltd. And the first part of my talks, the first 10 minutes, is a little bit to make you familiar with the idea of such a research company in Germany. So we are a little bit different organized than Max Planck, the speaker before. And in the second part, I want to introduce, again, about 10 minutes, what we are doing in the field of additive manufacturing. And then the third part, another 10 minutes, will be given by Ms. Haneen Daud. She's the head of our metal department, and she will introduce you what we are doing in the field of additive manufacturing, and especially also in the collaboration with a company in Vietnam. Therefore, in total, we have 4 parts, and I start to introduce to you this research company. And you see, it's a minister of economics in Bavaria who is funding this institution. You must see that Germany is subdivided in different states. And then again, the states are subdivided in local regions. And the region around the city of Bayreuth is very close to the former border to East Germany. Therefore, this area is not as well developed as, for example, the area around Munich in Germany. So this upper part of Bavaria we call Franconia, and Bayreuth is one city in Upper Franconia. And the idea was to bring new high-quality working spaces in this area. And I think this is also a need in several areas in Asia, that in states, some areas are not well developed. And therefore, I try to make a little bit advertisement for such a company which you set up in an area which is not well developed and which is doing research and development, especially focusing on the companies around the area where this research institution is localized. This means if you look on this video, or first on this picture, one moment, then you see this is the city of Bayreuth here in the background. This is a highway which connects Munich, Nuremberg, and Leipzig and Berlin with each other. So it's one of the major highways in Germany, connecting from Munich to Berlin. And you see here on the left-hand side is the University of Bayreuth, and you see here on the right-hand side this new material Bayreuth GmbH. This means both the university and this research institute are very close to each other. But in the past, there was always the problem that small companies, they don't think they are ready to talk to people at the university, because for many small companies, university research is far away from their practical needs. And therefore, the idea of such a research company is to bridge the border between the local companies and the university by having a company which is organized like a company, it's an LTD. And this LTD has a task to develop new technologies for the companies which are localized around the city of Bayreuth. And if you look on a closer view, then you see here we have several other research institutions. For example, we have here Fraunhofer Center, which is working on ceramic materials. You see here we have a Fraunhofer institution, which is working on process technology. We have a faculty for engineering science at the university, and especially a building where the professors working in metals, ceramics, and polymers are located in. So this research company by itself, I show you a small video, was founded in the year 2000. We have a center where we have administration and we can have presentations. We have a technicum, and very important in this technicum, we develop new technologies. For example, all these technologies around additive manufacturing, and this company is open to demonstrate these technologies to the companies around. This means if you look at this chain, then on one side is a university, here is the Neue Materialien Bayreuth GmbH, and here you see the connection to the companies around. Because we are affiliated to the Bavarian Ministry of Economics, we always get fresh money for new investments. This is different than to the university. The university is paid by the Ministry of Education. So as a professor, you get only money when you start as a professor. And then you have to live with this equipment, which you got maybe for 20 years. Here at this institution, we always get about 3 million euro per year for new investment in new equipment. And this investment has to be targeted to the companies around the location of Bavaria, of Upper Franconia. So the company was founded in March 2000. We have 3 divisions. One is on metals, one is on polymers, and the third one is a division which is run by the professors of the universities. Therefore, several professors from the universities are active in this company. And by this, they also get somehow money from the Ministry of Economics for their research ideas. So the operating expenditures are in the range of 5.8 million per year in 2020. And that's something what is very interesting, that the state of Bavaria invested in new equipment in the last 10 years about 26.5 million euro. Total number of employees is 60. So beside our technicum, the lab building and the administration building, we have one foundation center which belongs to the company. For example, we have a PhD students who developed a new idea on, for example, foam injection molding. Then this PhD student can start with his own company in this startup center. And for example, he can use the equipment from our Technica. This means he has only to pay the time he is running the equipment. And this is completely different as if you start with a startup and you first have to buy a foam injection molding machine, for example, for 500 million euro. Therefore, this foundation center is quite interesting as a startup center, which is directly connected to the Neue Materialien Bayreuth GmbH. So it's a it's a LTD, therefore the funding is 55% by the state of Bavaria, 15% by the city of Bayreuth, 15% by the Upper Franconian chambers, 9% by the University of Bayreuth, and 5 private persons. These are the division leaders, the CEO, and 1 professor from the University of Bayreuth. So it's a real LTD. And when I talk to you that it's mainly focused on the companies in the area around, this means in Upper Franconia, then this does not mean that this company is not acting worldwide. This means we have projects together with local companies and companies in China. And actually by GreenTech, we are now also trying to extend this to get in touch with companies, for example, in Malaysia, in Vietnam, in Thailand. So for us, the Asian area as possible customers for technology transfer are extremely interesting. So I already told you we have 3 divisions, one on metals, one on polymers, and in metals, we are focusing on additive manufacturing and on hydroforming. This means we have a huge hydroforming press in our company, and we do contact heating. In the division of polymers, we are working also on additive manufacturing. I will demonstrate you the center a little bit later. We are working on bead foam technologies. We are working on fiber reinforced composites with a special focus on composites with a thermoplastic matrix and not with the thermoset matrix. And we are focusing on new injection molding technologies. So in my talk today, I will introduce to you additive manufacturing, and later you get an idea about what we are doing in additive manufacturing in metals. And maybe for some people in Asia, this is quite interesting. So as I said before, there is a division which we call Future Solutions, which is run by the professors of the universities. For example, we have Professor Scheipel, who is active in the development of biomaterials based on spider silk. So, and if he has projects which are close to industry, then he is running within our Future Solution division the project because it's much easier for a smaller research company to work together with the companies and with the university. Even the contract work is much, much easier, and we can reduce the time until you start with your project. Therefore, other subjects are functional interfaces, are nanoanalytics, are nanocomposites, particle interfaces, polymer additives, polymer functional materials, thermosets. And what we hope that some of these fields, which are now groups, are later divisions within the company. Now, coming back to the mission of the company, it's technology transfer. So this means things which are developed within the company, but for example, also in collaboration with the university. These technologies we want to share with other companies. And when we say we are sharing the technologies, then we are also sharing the infrastructure. This means, for example, we have a huge automotive supplier close to Bayreuth. And this automotive supplier decided to start in the field of thermoplastic composites. And this was 10 years ago. 10 years ago, these people went to the Ministry of Economics in Bavaria, and they get the okay from the ministry that the state of Bavaria is investing in the infrastructure to develop thermoplastic composites for automotive industry. And therefore now this infrastructure was not set up in this automotive company, it was set up in our research company, and we had joint projects with this company, but also with other suppliers of automotive industry. So therefore this high risk project, because none of these companies really know before they start if they will really have a business later in this field. And therefore, we take the risk of starting something new to a research company, and other companies working in the field, they can use this equipment and they can develop their own demonstrators. Now, by collaborating to each other, you're also exchanging ideas, and then you are getting closer and closer to each other. In addition, within our company, we also have networks For example, there is a Upper Franconian plastic networks where more than 100 companies are involved in the network. For example, subject of this network is how can I save energy, for example, by injection molding, which technologies I have to apply to injection molding to be more sustainable. But we have also a network which is focusing to promote one material. For example, there is a version of polystyrene foams. They are called EPP, is a polypropylene foam. And there's a network of all the companies which are working with this EPP material. And they all together want to compete against other materials. And therefore, if they are within a network, they are much stronger as if an individual company is trying to get a business. Therefore, networking is a very important part of this research company. So the basic idea is this bridging function from research to real production. We focus on new materials, we focus on new processes, and it's very important to bring the right people together. So for the collaboration, we have different types of projects. For example, there could be an order for tensile tests from a local company, so they don't have a tensile test machine. This is the simplest way. But there could be also a collaborative project where, for example, 5 companies are working together. Our company is a partner of these 5 companies, and this project is funded by 50% by the state of Bavaria or by the German government. And there's a third version where companies want to do a direct project with us, which is 100% paid by the company. And for these types of projects, it's very clear that we don't publish this work. This means the intellectual properties belong to the company who is in our contract partner. Therefore, in summary, the idea, which is maybe one very fundamental idea, might be developed at the university, for example, by projects which are funded by the German Research Foundation. So these projects at the university are far away from an industrial partner. But if we get closer to application, then these project ideas, for example, we can fund by the Bavarian research institutions or by the Ministry of Economics of the German Republic. So therefore, as closer you get to a real business, as less is the funding by the state. But in total, with the university, this research company and our industrial partners, by running co-joint projects, we are extremely innovative and also fast. We have a very fast working chain. Therefore, I put the French TGV here on top of this bridge. Now, looking on the field of plastics, polymer science has a very long history at the University of Bayreuth. And with this slide, I only want to show you that at the university, there are more than 20 professors working somehow on macromolecules. And this includes polymer synthesis and catalysts, polymer characterization, interfaces, biomaterials, and so on. Therefore, the research company NMB has a chance to use all these experts to run projects because we are so close to each other. In addition, we have the Startup Center, and I only want to mention that in Bavaria, we have more than 50 startup centers. And within these 50 startup centers, we have actually 100 companies which are growing. And these 100 companies in total generated 5,000 working places. And if you look only on the NMB Startup Center, we have all these companies in our startup centers. These are small companies, but they use the infrastructure of our company. And in addition, we have this network, the Kunststoff Network Franken, I already mentioned, but there is this EPP forum, which is focusing on materials. And there's, for example, Bayern Design, where we try to combine design of a product with new materials.
If I may just remind you, we have 15 minutes left now for you and your colleagues in total.
Okay, so then I go a little bit faster to our research center on additive manufacturing. What you see here is the logo of a company which is called PP Print. And this company, PP Print, is focusing on extrusion-based 3D printing. This means within the company, we have a specialist for providing a full range of materials, accessories, and technical support for 3D printing of polypropylene, because polypropylene is somehow the working horse under the plastics. And therefore, they deliver, for example, polypropylene filaments in different colors, pellets, and these filaments for additive manufacturing. So within our demonstration center, we have analytics. We have different types of 3D printing accessories. For example, we have the Arborg freeformer, we have selective laser sintering, and we have the FFF printers. And by this, we can do part printing and analytics on the parts. And this equipment is focused on 180 square meters of additive manufacturing. It's an experimental lab for the regional industry. These people can come and check which of these different technologies are best suited for their applications. Therefore, we do research, consulting, and design. And this includes, for example, new materials, new functions, high-performance thermoplastics. This includes process development. This includes also large area manufacturing. We can print parts up to 1.50 meters height. And also the combination of different processes is of high interest. So looking on the time, I'm stopping here and I hand over to Ms. Haneen Daud, which tells you a little bit about what we are doing in the field of additive manufacturing with metals.
Thank you very much, Mr. Professor Alderstadt. I think you can see my presentation.
Can you switch to the, yeah, perfect.
So I'm very great to have the chance to present the innovations from the Division for Metals at the Technology Center New Materials Bayreuth. As you heard from Mr. Professor Alderstadt, we have a long years of experience in this field. Since 2010, we started with simulation and modeling. And after that, we focused on the development materials and the process for printing of metals. For example, we developed two different processes like diffusion bonding and direct energy deposition. For today, I will start to show you an example about our self-developed wire-directed energy deposition process. And after that, I will finish my presentation to show you an overview for our investment in 2022 in the field of selective resin melting. So our self-developed directed energy deposition focus on the use of two wires. Here you can use the same or different type of materials combined with a high laser power, for example, 2 kilowatts. We have also different functions like the preheating of the wires and the preheating of the carrier plate. The question is why we considered that our process is different and even is better than the commercial available process. The first reason, because our process is worldwide, the only process is carrying out under vacuum. So this means that the oxygen level will be always very small. The second point, and this is as a result of the using of the preheating of the wires combined with the preheating of the carrier plate, you will not have any crack formation by the printing of different metallic components. Or because we use a high laser power and also high preheating temperature of the starting material, we will have high building up rate. And as I mentioned before, we can optimize and develop different composition of the target alloy during the process by using different type of materials at the same time. Here you can see an example. That is state of the art, a printed component or a part made from titanium alloy. You can see that there are a lot of oxide level, and also you will have stresses and cracks in the whole part. By using our self-developed process, you will not have any more cracks, and the oxide will be eliminated. And this is the benefit from this process. I will not show you too many examples or results. I'll summarize it. If you print a small component with a length of 1 centimeter or a large component with 30 centimeter, you will have everywhere the same and homogeneous microstructure. And this is totally different from the state of art. You will have heterogeneous microstructure. Oxygen level will be always lower than 0.02%, and this is very low. The building up ratio is in between 150 to 600 square centimeter per hour. And this is very speed and very comparison to the state of art. The question is where we can use this process. Generally, if you have simple to middle complex component, or if you need to print whole components, you can use it, as you can see here. Here you can see we can print some truck exhaust valve from different materials, beginning of steels and also titanium alloys. And in this area, we received already a request from a company from Vietnam, and they would like to test our process and print some component in this direction, and we will do it 2022. You can also print in under the top of target material, for example, airframe wing spare, or you can print components. They are no longer deliverable. For example, here we see this is wheel set bearing cap from locomotive, and they are no more available. With our system, you can print these components. There are too many applications for our process, but they are not limited for what I presented for you. Now, I will start with the second and the last example, when this is our investment in 2022. We have now a small machine for selective resin melting. When we decide to invest to buy any new machines in 2022 to have a high laser power and high building space. But the question is why we decided to have this investment. During the last 3 to 4 years, we got a large number of requests from different companies in Germany and also from Europa that they need to print different metallic components. They are not made from steel, This means that we need a different and higher laser power, and also they would like to print small to medium-sized components. To achieve this aim, or these aims, our investment will be focused that the new machine will have a high laser power with a preheating temperature above 200 to 1000 degrees Celsius to be able to print different metallic components starting off nickel, titanium, cobalt, and even molybdenum alloys. I will show you two different examples. They are coming from companies from different application areas. With a new machine, we will be able to print vacuum-tight components from molybdenum. They will be used as a caps in electron microscopes, and they should be vacuum-tight. And where molybdenum is not easy to be printed or to be machinable. You need a high expensive tools with selective laser melting will be able to print such these components. The second and the last example in my presentation is to print toroidal metallic components with a smart design. Smart design, we mean that, for example, you will have efficient cooling rates. Here you can see an example. This is an extrusion head for extrusion of different polymers on the plastics. With this word, I will end my presentation, and I hope that you enjoyed and are interested in our innovation. Thank you very much.
Thank you so much, Professor Alstedt and Dr. Daoud. May I now invite Henry Wu, the president of APEC Vietnam, to share with us the view of an industrial company on why are you collaborating, Henry, with research? What is your interest in 3D printing, and how will it help you to make your manufacturing more competitive and more sustainable? Thank you.
Hello.
We can hear you. Thank you. We can see your screen.
Good afternoon, all member, speaker, and I am very much appreciate for all of the information sharing today. So today I am very happy to be present and representative for the APAC groups, and would like to present some general demand in the near 10 years in the APAC market, and one of the core market segments that we are focusing. So in order to easy for you follow, I would like to have a short introduction who we are and what we are business. So I come from the consultant and management community of the APAC groups, and APAC groups is the international company. We have the representative around the APAC region. We have the 3 core of the regional office in Vietnam for ASEAN region, Australia, and United States. And I currently mainly full-time in United States now. And we are focused on the almost 20 industry. And what is the business model we are dealing? We have been the survey market and business development for the APAC forums. And after a long time that they're working with there and the data that we collect from the APAC region, we find out that this is one of the very good market, and the business model should be changed from the normal into the new frameworks. So we are one of the economic groups that we ambitious to forming the new platform for changing the supply chain for the APAC region. And we understand that the small or the medium enterprise, they cannot do themselves own thing from the production, R&D, and market. Or even like Professor Volker mentioned about it, cannot talk directly with institute or university when we think about the R&D activity. So IPAC group would like to be like the pointer people, and we come and talk and engage relationship from the enterprise for manufacture and institute and university for R&D. And we also jump into the market. So currently we have almost 4,000 Salesforce system around APAC region. And that's one of the core people that could have the feedback of the what is the market demand. And we believe that throughout those people, and if we could integrate with the institute like these programs and university and the manufacturer in Asia, we hope in the near future we have the good platform and restructure of the new supply chain, especially from the APAC market. So in the supporting industrial, we think that that's nothing different with the Europe or some other country when they develop the product of the industry. So for the ASEAN or the ASEAN market or the APAC market should become from the one of the core of the supporting industry field. And we should have the plastic and rubber or mechanic or textile, leather, electronic, information of food or medical, healthcare, saving energy, GreenTech, or so like water, air processing. So indefinitely, right now, all of the above field, industrial field, we are focusing. But one of the limitation that we cannot go faster is the connection, and the limitation because in 2020 the COVID starting. So IPAC just starting in step by step. So far up to now. So we come into what is it that we have connection from the ASEAN and the US market in follow industry. Like we have some product in the gearbox industry. And currently we are work with that field for one partner that they provide a facility for military of US. And the second one, we work with the freight line spare part for some kind of equipment and part inside of the truck. And for the plastic and rubber, so we are dealing with some partner in Asia and one in Europe in the Aerosol. And you know, one of the Aerosol is one of the very big enterprise in Europe. They have a lot of products, and now we are success in the design the master box and making the complete products related to the plastic, technical plastic in Vietnam. And we also one of the enterprise that we success in linking to almost 220 plastic enterprise from Japan that invest in Vietnam. And now we link all of this system into one ecosystem. And I think that's model also similar concept with expectation from the what Dr. Volker mentions. So we hope that with the short introduction of what we are dealing now and the opportunity to have the information from all of the professors sharing. So I think that's it, a good chance that we're starting to design some active programs or the appropriate projects for real the cooperation between the know-how or system in Europe and the manufacture system in Asia or APEC markets.
Okay, thank you so much, Henry. And
yeah.
if I may just ask one last question to you and one last question to the colleagues from NMB. Do I understand you right, Henry, that you're saying that 3D printing is one of the technologies which you need in order to introduce more sustainable technologies based, for example, on the engines which you have shown and other things? So where's the value of 3D printing for you? What tangible value does it add for you, for your operations?
We, in fact, as all people know, the world supply chain system is now changing. So it's not it will changing from like China, from Taiwan into some other country. It's like in the Mekong economic region, like Vietnam and some other economic in ASEAN. And all of the APEC or the ASEAN company, they are new with this. They would like to join with this field, but if we come back with the traditional manufacture, like we make the one equipment, we should have come from the die cast process into the complete products. It should come many steps, like from the design material, select the kind of material, and then making the mold, and then come into the detail of all the precision processing. So we think that with the advance of the additive technology, 3D printings is very, very good, and I think it can cut very short time for us, especially for now the time that we talk with the new clients, the new opportunity. So we should have shortest as much as possible the time to provide the prototype products to the clients. So if we can implement or we can use some kind of from the 3D for making the sample or prototype to shortest, or in the future when we mass production, if we can have the good the cost of the manufacture, like the raw material or the model or general shapes of the products, and then we come into the detail processing. I think it also better instead of we implement the traditional methods.
Thank you.
Yeah, I think it's not only in the mechanics and many on other especially for the plastic, technical plastic, very high demand with this one for many implementation. And we also involved in the water processing. So we need a lot of the material and the part that support it to do that. Even in US, we also now should be moved from the traditional manufacture of the fiber optics or some kind of equipment from the injection mold into the 3D printing.
Thank you very much. And then one last word, maybe from you, Professor Altstedt, about what is the contribution to sustainability of 3D printing?
Oh, I think as less parts you need, as higher is the contribution to sustainability. And I think the most sustainable way is to, for example, to make conventional methods and then to individualize by 3D printing. This means, for example, if you need a special fixture on a plate, then you can produce 300 million plates, very cost efficient, and then the individual fixtures you can print on these plates. Yeah, and so you save a lot of energy if you can produce something in mass production. Yeah, but very often mass production doesn't work because you need, in some places, individualization. And this you can do by combining both.
Thank you. Okay. Thank you so much, all of you. And we have overdrawn now our time budget already by 9 minutes. I apologize to you, Susanne, for that. And I will spare you a fast word now, but for me at least, all these presentations were absolutely fascinating and they make me very optimistic about the future of EU-ASEAN research and innovation collaboration. Thank you all so much. Susanne, would you like to say a last word?
Yes, thank you so much, Michael, and thank you for all the speakers for a really very exciting session. We've seen in the chat, there's obviously a lot of interest from other researchers to join forces with you. And I know that Michael will make sure that everybody gets connected. We've already said we will share also the recordings and the slides with everybody who's in the session today. And of course, we'll make it available via our YouTube channel to make sure that even more people hear about this project and hopefully get in touch with you to expand it even more. So with this, I think from me and Jenny, thank you so much for excellent session.
I have to say something quickly. I have to really spotlight Professor Hanid Daoud, because being an excellent scientist, women, especially a woman in science in a field that's not that filled with women, and now seeing that you are also balancing it off as a mom, it's really empowering, and this is exactly also what EU wants to promote. So gender in science and women empowerment in science, yeah, that is what you get also with this discussion. So thank you so much for joining us.
Yes, thank you so much, and have a wonderful evening and a good night, everyone. We'll see you all very soon. Thank you so much.
Thank you so much. Bye-bye.
Thank you.